We're starting now. We have a new session today, Causality. Here with us is Joris Mooij from the University of Amsterdam, a very renowned expert. So please welcome him, and let's start with our session.
Okay, good morning, everyone. This session will be on causality. And as you may know, many questions in science are causal. So, for example, climate researchers, they want to know. By the way, can everybody hear me well? Is it too loud, or it's okay, I guess? And okay, another thing I should say: if there are urgent questions, then feel free to interrupt me along the way. Okay, so climate researchers, they want to understand how the effects of, say, greenhouse gas emission on global temperature, and then also the effects of our policies on greenhouse gas emission. Also in economy, causal questions are very important. For example, here, whether cuts in spending, whether that causes higher unemployment or not. In medicine, of course, you want to find a drug for a disease. So, what is the causal effect of a treatment on an outcome is a very central question. On health outcome is a very central question in medicine. And in neuroscience, we can nowadays measure the activity of different regions in the brain and make very nice pictures of it. But at the end of the day, we would like to use this data to understand how the brain works, so how the activity of one region in the brain influences the activity of another region in the brain. Causality is clearly an important notion in science, but also in daily life. But how should we formalize this notion of causality? And how should we reason about it? How can we discover causal relations from data? How can we use this to make causal predictions? And how does this differ from the predictions in machine learning that we are more used to, maybe? So that's basically what this tutorial is about. In traditional statistics and in machine learning, we often use probabilistic inference. And there we model the distribution of the data. We focus on predicting the consequences of certain observations. So, for example, in medical diagnosis, if a doctor sees a patient, then a relevant question is, given the observed symptoms of the patient, what is the most likely disease? And that we can do, that question can be answered with the standard probabilistic inference methods. For example, using Bayes' theorem, just as an example. In causal inference, on the other hand, we have to do a bit more. We try to model the mechanism that generates the data, and also how this changes under certain interventions. And this allows us to predict also the results of interventions. And this is then useful, for example, in medical treatment. So if we treat the patient with a drug, will it cure the disease? And that's really a causal question, and that goes beyond this standard probabilistic inference based on observations. So basically, you could say that causal reasoning is actually essential if you want to answer questions of this type. Given the circumstances, what actions should you take to achieve a certain goal? Okay, so this is the outline for today's and tomorrow's tutorial. We'll start with a more informal discussion of causal modeling, and we'll do this using causal graphs. And then later on, we will make things more rigorous and be able to quantify things. I guess you all know that causation is not the same as correlation. And here is a nice example that illustrates this. So here you see data, a scatter plot of data from various countries. On the x-axis, you see the annual chocolate consumption, and on the y-axis, you see the number of Nobel Prize winners in the country, normalized by population size. So what you actually see is that there is a significant correlation between the two. But does that also imply that if you are trying to earn a Nobel Prize that you should eat lots of chocolate? Or maybe the other way around, that if you win a Nobel Prize, then you give such a big party where a lot of chocolate is eaten that it influences the chocolate consumption in the country. Well, I guess the answer, so does anybody have an explanation for this observation, this correlation? Anybody has an idea?
Maybe just about the health level of the country, that chocolate is a luxury product, and so you have more money for institutions and education.
Yeah, exactly. So that seems a plausible explanation of this, that wealthy countries, there's more money to buy chocolate and also more money to spend on education and research, and thereby to win a Nobel Prize. By the way, there's an interesting outlier, Sweden. I'm not sure why that is, but... okay, so if causation is not correlation, then what is it? So here's an informal definition. So if we have a system and we have two variables in the system, x and y, let's say, and we say that x causes y if changing x leads to a change of y. So causality is really about changes on the system. Okay? So if we all eat more chocolates, do we have a higher probability to earn a Nobel Prize, for example? And we can use a causal graph to express these causal relations between variables graphically. So here are different examples. Unfortunately, I'm used to point with my laser pointer, but here I have to use the mouse. So here, for example, it's even challenging to use this mouse. In this example, x1 and x2 are causally unrelated. Here, x1 causes x2, which is why there is a directed edge pointing from x1 to x2. Here it's the other way around. We can have both simultaneously, that they're causing each other, usually. Here there's a common cause x3, so for example wealth causing chocolate consumption and Nobel Prize winners. And here they have a common effect. So these are just various examples of causal graphs. Okay, but then to explain more precisely what the directed edges in a causal graph mean, we have to introduce this notion of direct causation. So now, suppose we have a set of variables, we have n variables, then we say that one variable, xi, causes xj directly with respect to this whole set of variables. If we keep all the variables fixed, and then still changing xi leads to a change of xj. Okay? So we can, so here in these examples, sorry, I have to point again. Here, in this example, x1 causes x2 directly even. Here, also x1 causes x2, but not directly, because basically x1 causes x3, and then in turn x3 causes x2. So here there's no direct effect of x1 on x2. So if we would fix x3 to a certain value, then a change on x1 would not lead to a change of x2. And we can have both of them combined as well. So here is a simple example. Suppose we have a row of domino stones, and each stone causes all the subsequent stones to topple, right? So that's the indirect causes. But each stone only causes its immediate neighbor stones directly, right? So that means that the causal graph for this row of domino stones would look like this. So we only have direct edges between each stone and its direct neighbors. And actually, this is already an example of a cyclic system, because the causation can go in two directions, right? We can let them topple to the left or to the right. Yeah, and suppose we now intervene, for example, by keeping the second stone fixed in the upright position. For example, by gluing it to the floor, then you can see that the neighbors, x1 and x3, they no longer have a direct cause on x2 because it's fixed. So that changes the causal graph in the way that you see on the slide. Yes? Because, yeah, so thank you. Good. So the question is, why does x2 still cause x1 and x3? That's for this example, if it's really fixed, then you could say, well, that it's a constant, so we can disregard it. But you can still think of overriding the intervention. So if I really strongly intervene on x2, such that the glue breaks and it will topple, then we will still see an effect on x1 or x3. So that's why. Yes, another question?
If I understand correctly, the causal graph, you don't only write what happens, but what could happen.
Exactly.
Observed events, or unobservable events.
So what do you mean with unobservable events?
I'm not sure, I'm just trying.
Well, so for the domino stones, so causality is about how external events change a system. And so we always, basically, in order to, we always have to consider a certain set of interventions. So at the end of the day, we are also modeling certain interventions. So maybe an earthquake is not, that intervenes on everything simultaneously. Maybe that is something that we would like to consider, maybe not. But in general, we will also formalize the notion of intervention. And in that way, we will only have expected possible changes. I'll tell more about that later. Actually, here, later, this is now the moment to introduce perfect or surgical intervention on a system. This is an important concept that we will see again and again in this talk. So suppose we have a set of variables in a system, then we can intervene on a subset of the variables in the system and giving it a certain value. In the previous example, we intervened on the second domino stone and gave it the value upright. Basically, this intervention is perfect because we imagine that we only intervene on a specific part of the system, and the rest of the system is not changed by the intervention. So we are sort of relying on this notion of modularity here, that we can divide a system into two different parts, and we can change one of the parts and leave the other part untouched or invariant. So that's an important underlying assumption here. And if you make that assumption, then you can talk meaningfully about these perfect interventions. Yes?
But in the touch part, we can, things could happen, like change, that we don't intervene on this part, right? So I mean, like the untouched part,
Yes?
things could happen, so things could change. But without
Later on, you mean?
Without any intervention.
So no, the idea is that we have a system, and for example, it's modular. It's built out of pieces. For example, the domino stones, they are different pieces, and we can think about changing one piece, but not touching the other pieces. And if we can do so, then we can talk about intervening on one of those pieces. If this is just a sort of a system that is just one blob.
Talking about human intervention, but it could be like the wind, could be something that could change.
Yeah, so it's not always possible to have these perfect interventions, but if we can imagine them at least, then it may be meaningful to model them. And that's what we are going to do. Okay, and note that this intervention changes the causal graph, as we have seen, by removing all the incoming edges to the intervened variables, right? With the example, intervening on x2, removed from the graph all the incoming edges. Okay, another important concept, the concept of confounder. So basically, a confounder is a latent common cause. That's the loose definition. More precise definition is that if we have three variables x, y, and h, then h confounds x and y if h causes both x and y directly with respect to these three variables. So here are a few examples of confounders. So in all these examples, except the one with a big red cross, h is a confounder of x and y. So you see that there could be complicated other things going on, but what is important is that if we only look at h, x, and y, then there's this causal effect of h on x and y. And here this is not a confounder. Oops, here h is not a confounder because there's no direct effect of h on y. Right? It's only mediated via x. Yes?
It's a bit of whereas h effect on x and y with h2 and h3, it's not direct.
So yeah, that's a good question. So the remark is here that in this example, the effect of h is not direct on x and not direct on y if we look with respect to all the 5 variables in the model. But this is the important point about direct causation. This is always relative to a certain set of variables that we consider. So if we don't consider h2 and h3, then actually there is a direct effect. Later on, I will formalize this, and then you can easier see when we have a direct causation. So this is a bit tricky. That direct always, it's not an absolute notion. It always depends on the set of variables that you consider. Okay, so here's an example of a confounder that we have already seen. Right? Wealth may confound chocolate consumption and Nobel Prize winners. Okay, now since confounders can be latent variables, maybe we don't even know that they exist. And so we don't usually have that much information about them. We introduce this sort of abstraction using bidirected edges in the causal graph to denote confounders. So, so here, a bidirected edge between x and y. This is basically an abstraction of many different possible causal graphs that have one or more latent variables in addition to x and y, where there's always one latent variable that has an effect on x and y. So for example, here h is a confounder, here also h is a confounder, in addition to all the complicated causal relations that there might be between the latent variables. And you can have such a bidirected edge in addition to a directed edge between x and y, or even in addition to two directed edges, so a cyclic causal relationship. So already for two nodes, two variables, x and y, you can see that there are many possible causal graphs in this way. But okay, I think there are 8 in total, so it's not too many. If we were to explicitly model latent variables, because that's another way that we could go about this, right? If we say, there could be latent variables, let's introduce one latent variable in our model, or 2, or 3, then the problem is that we have, in principle, infinitely many latent variables that we might need to consider. So in a way, just representing all of them with this bidirected edge if they lead to a confounder. That's really a nice summary of the latent space. Basically. Okay. Another causal concept that we already saw, that's causal cycles. So if we have two variables in the system, and if x causes y and also y causes x, then they form a causal cycle. And here's one prototypical example. Suppose I have two masses and I connect them with a spring, and I also connect the upper mass to the ceiling with a spring, right? So like in the picture that you see there, then if I would wait until the oscillations dampen out, then if I intervene on the position of the upper mass, if I would sort of pull it down, for example, then the lower mass would also change its position. But also, if I change the position of the lower mass, that would lead to a change of the position of the upper mass, right? So the causal graph of these two is what you see in the picture. The two positions cause each other. So if you only restrict yourselves to acyclic causal models, then you can't really model this system very well, or at all. And cycles are actually very relevant in many systems that you encounter in the real world. For example, in climatology, there are cycles like if the sun shines, then sea ice may melt, and then white turns into blue. And blue actually absorbs more light, so the heat increases even more. More sea ice melts, and you get all these kinds of feedback loops. In biology, in the human body, for example, there are also many feedback loops to regulate things. For example, your body temperature is regulated at more or less 37 degrees by a feedback loop. So being able to account for cycles is important when we try to make sense of the many systems in the real world. I'm saying this because actually in the causality literature, most of the literature just assumes that there are no cycles and considers acyclic models. In recent years, we have made quite some progress in understanding cyclic systems, and actually in this tutorial, I'll also deal with cyclic causal systems, because I think that's important. Graph terminology. Yeah, so I have introduced these causal graphs that have two types of edges, directed edges and bidirected edges. And in general, such a graph is called a directed mixed graph. Why mixed? Because it also has these bidirected edges. It has two different types of edges. Yeah, if we, in such a directed mixed graph, we start at a node and we follow the directed edges and we end up at another node, then we say that the first node was an ancestor of the former node was an ancestor of the latter node. And we notate this like that. I1 is an ancestor in graph G of node IK. And we also say that there's then a directed path from I1 to IK. So this is an important concept that we'll see many times, so please remember it. Such a directed mixed graph is called cyclic if it contains a directed cycle, where you see an example of this notion here, which is basically a directed path starting at a node, going to a node, and then a final edge that brings you back to where you started. And all these have to be directed in these directions. So bidirected edges cannot be part of a directed cycle. Yeah, strongly connected components. Well, let's skip that for now. Yeah, some more terminology to connect to the literature. If the graph is acyclic, if it doesn't contain directed cycles, then it's called an acyclic directed mixed graph, ADMG. If it also does not have any bidirected edges, then it's called a directed acyclic graph, or DAG. Okay, so this was sort of an informal introduction to causal modeling using causal graphs. directed mixed graphs. Are there any questions before we continue with formalizing this a little bit more? No? Yes.
Considering the strength of the relations, in your spring model, the stiffness of the springs would affect all these sort of.
Yeah, so that's so the question is, do we consider the strength of the causal relations? Well, in the part up until now, no, we didn't. It was just a yes or no question. Is there a causal relation, yes or no? In the structural causal models that I will now introduce, we quantify this more, so we can distinguish strong and weak causal relations, etc. This will all be quantified. Yes? Bidirected edges, by definition, can't be part of cycles. So a cycle, by definition, consists only of directed edges that all point in the same direction, basically. So you keep following edges pointing in a certain direction until you return where you started. Yes, one more question. Then it's no longer a directed cycle, but it could still be a cyclic graph if there are other cycles in the graph. For example, here, if we just, there's this marine coupling feedback loop that I just described. If we replace one of the directed edges by a directed edge, then there's still another cycle here, terrestrial coupling. So it's still a cyclic graph then. Okay, so structural causal models. So so one of the natural things to try is to define causality in terms of probabilities, right? So we know that the world is uncertain, so maybe we can talk about, when taking into account this uncertainty, maybe we can use probabilities to define causality. So a naive attempt could be like this. Suppose you have two binary random variables, A and B, and suppose we know that A happens earlier or A describes an event that happens earlier in time than B. And in addition, if the probability, if A is true, then the probability that B is true is higher than when A is false, right? So A being true increases the probability of B being true. Then you could say that A causes B. So this is an attempt as a definition. But this definition doesn't really work. And you can see this clearly by a phenomenon that's known as Simpson's paradox. And did you all get the handouts meanwhile? Yes, I hear paper whistling. So please make exercise 1.1. Should be a quick exercise, a few minutes or so, that will show you Simpson's paradox. Because it's best to see this with your own eyes, basically. I think, I saw that many people are done. Are there still people who need a bit more time? 1 or 2 minutes? No? Then let's discuss this. So what you just saw is this scenario here. So suppose we collect electronic patient records or some data from some source to investigate the effectiveness of a drug against a disease. Then you can actually find the numbers such that the probability of recovery is higher for the patients that took the drug. But if you then subdivide your patient population into two disjoint parts, for example, males and females, then the relation is the opposite. So for both males and females, the probability of recovery is lower for those that took the drug. So then, using this probabilist, so the question then is, does the drug cause recovery? So would you use the drug if you are ill? So who here would use the drug if you have the disease? Can you raise hands if you would use the drug? A few people. And who would not use the drug? Everybody else, I guess. So who would use the drug? Can you argue? So anybody has reasons why they would use the drug? No one? Anybody can motivate why they would not use the drug? You were nodding? No. I don't understand you. Can you speak up? I don't understand you. Yeah, so if you consider that, so if you don't consider gender, then the recovery rate is higher if you take the drug than if you don't. But if you only look within a certain subpopulation, say only the males, then it's the other way around. So that's the paradox, right? What's going on here? So interestingly, the numbers in the example, they were quite small. So you could think, well, maybe if we have millions of patient records, then surely we should be able to figure this out. Well, if you just multiply all the numbers by 1 million or 1 billion, it doesn't really help. The fractions still remain the same. So big data here doesn't help you. Neither does deep learning or whatever fancy machine learning algorithm you might want to throw at this data. So it's really a fundamental question here. And actually in this tutorial later on, tomorrow actually we will revisit Simpson's paradox, and then hopefully you will understand how the paradox can be resolved. So problems like these have sort of historically prevented statisticians from considering causality, I think. But in different disciplines, different approaches came up to model causality and to reason with causality. So there are three important frameworks in the literature nowadays. The potential outcome framework, mostly in the statistical literature. Causal Bayesian networks, that's mostly in AI, and Julia Pearl's work and others, but also structural causal models. And that's kind of related with causal Bayesian networks. And in this tutorial, we will make use of these structural causal models, because in a way you can argue that they are the most general of these three. So using structural causal models, once you understand structural causal models, you can also relate to the other approaches. But in the other direction, it's more difficult. And there are some nice features of structural causal models. They can model cycles naturally. So there's a close connection with dynamical systems described by ordinary differential equations. For example, these oscillating masses. This is a textbook physics example of a dynamical system that you can describe with Newton's equations of motion, for example. And they are closed under marginalization. So this means basically that if we have a description, a model for a large system, then we can sort of project it down onto a model that describes only a part of the system, a subsystem. That's also a very nice feature. They can also model counterfactuals. And in that sense, you get an alternative to the potential outcome framework, where basically counterfactuals are the starting points to formulate everything. And they generalize causal Bayesian networks. Yes? I will explain that in detail later on. Yeah, this is just to mention a few features, and this will be explained later on in detail. Okay, so basically, if we can't define causation in terms of probabilities, then maybe we need to turn things upside down. We will start with a causal model and get our probability distributions from the causal model. And thereby we will be able to avoid traps like Simpson's paradox. So here is this, here we get, on this slide you see the elements that play an important role in a structural causal model. We describe the system by endogenous variables. Those are usually observed variables. And they will be modeled with so-called structural equations. That's where the name comes from. And the environment of the system will be described by exogenous variables, and they are typically latent, that means unobserved. We model them using probability distributions, so not using structural equations. Important is that they are not caused by the endogenous variables. So typically we have an environment that may somehow influence a system within the environment, but we assume that the system does not influence its environment. That's very important actually in this modeling framework. And the exogenous variables, basically they provide the source of the randomness. So the structural equations, the system itself is sort of deterministic, but the exogenous variables, that's where we can put in randomness. And yeah, each endogenous variable has its own structural equation, which basically describes how this variable depends on its direct causes, which can be other endogenous variables, other variables within the system that directly cause this variable, but also exogenous influences from the environment. And as we will see, we can equip these structural causal models with a notion of perfect intervention, and in that way we get a causal semantics. How does the model change under interventions? Okay, here's the simple example. So this is an example of a car. Actually, I once had a car that is realistically modeled by this. So we have three endogenous variables. Whether the battery is charged, that's X, and Y is whether the start engine of the car is operational, and S is whether the car starts. The causal graph, as you quickly realize when you think about it, looks like this on the right-hand side, top right-hand side. So whether the car starts is a simple function of, or is causally influenced by whether the battery is charged and whether the start engine works. And to make it a bit more interesting, there is some uncertainty in this system, so we can introduce three exogenous variables. Let's take them to be binary and have Bernoulli distributions with some probabilities. And then we have the structural equations. So we have one structural equation for each endogenous variable. So X is basically expressed here as a function, f of X, which takes one argument here, e of X, an exogenous variable. And the function is very simple, it's just the value of e of X. So this is kind of, by saying this, is that basically e of X is some kind of unknown factor that basically defines whether the battery is charged or not. Right? So this could be a summary, an effective summary of many things, like what did you do with your car the day before, or what is the temperature outside, or all those things. How old is your battery? All of this is sort of absorbed within a simple random variable e of X that will tell you whether the battery is charged, yes or no. We have something similar for the start engine, and then, so that's not really the interesting part of the model, it's slightly more interesting here when we define the structural equation for S, which is now a function of two endogenous variables, X and Y, and one exogenous variable, E of S. It's basically the AND of those three. So the car starts if the battery is charged and if the start engine is operational, and if other unspecified factors are satisfied. So this was an example of how a structural causal model looks like in general. So they go back to Wright, almost a century old now. Wright used this for genetics originally. He was a geneticist. So basically, a structural causal model formally consists of 4 things. We have a standard measurable space that describes the possible values of the system variables. So this will be always x. And I will always use an index I for the system variables, and a calligraphic I to denote the sets of indices for the system variables. We also have standard measurable spaces for each of the exogenous variables that will be denoted by this calligraphic E. And then the important part is the causal mechanism. This is a function, a measurable function that just maps tuples from endogenous and exogenous variables to endogenous variables. We'll see how it plays a role in a moment. And finally, we need a probability distribution which factorizes over the exogenous variables. So the exogenous variables are assumed to be independent here, and that is called the exogenous distribution. And so this is just a bunch of mathematical objects. The important part is how this defines at least a probabilistic or a statistical model is in this definition of a solution of a structural causal model. So if we have 2 random variables, x and e, then we say that they form a solution to a structural causal model. If the e variable has the right distribution, the exogenous distribution is specified by the SCM, and if the structural equations hold almost surely. No? No. What happened here? They're of this form: x equals f of x comma e. So we saw an example of that on this previous slide here, right? Are there any questions about this? This is sort of an abstract definition, but the big I and the big J, yeah, those are the indices of the variables. So big I are the indices of the endogenous variables and big J for the exogenous variables. So here, yeah, there were no indices here, but usually we enumerate them 1, 2, 3, whatever. Yes? The exogenous variables are always assumed to be independent. Yes, that's an important modeling assumption made here. You could say, well, then what if they are actually dependent? Yeah, so basically if you have 2 dependent exogenous variables and one that's independent of those 2, then basically you can group those 2 together and consider this as a single variable, and then so basically you can always find the largest independent components of your exogenous variables that are independent to satisfy this modeling assumption. And if you're unlucky, then it will just be everything concatenated together. But okay, here's another example of a structural causal model. So formally it's specified, formally it's specified by these 4 mathematical objects. Informally, in practice, we usually write down the structural equations, for example, like this here, and we write down the distributions for the exogenous variables, so like this. So here we have 5 endogenous variables, x1 to x5, also 5 exogenous variables, although in general their number could be different, e1 to e5. We specify the distributions of those exogenous variables, specify the structural equations. So these 5 functions here are the components of the causal mechanism. And as you can see in practice, the different components of the causal mechanism, they have different dependencies. They do not depend on all the variables typically, but they have a certain structure. And this structure is what we can express in the graph. So for example, x2 here depends on E1 and E2. So in this augmented graph, we have depicted the endogenous variables, the x's, and also the exogenous ones. And here x2 was a function of E1 and E2. So that means we get an edge from E1 to x2 and an edge from E2 to x2. For x4, for example, depends on x1, x4, and e4. So you see that x4 depends on x1, x4. Interestingly, it depends on itself and on e4. So this is basically this notion of an augmented graph that you can read off from the structural equations. You can also choose to not draw the exogenous variables, and then we just call it a graph. So then you get this object here. And then we basically use bidirected edges whenever we have a shared dependence on some exogenous variable. So x1 and x2 both depend on E1. That's why we have a bidirected edge here. Okay, so now you sort of start to see coming the pieces together. The causal graphs that I talked about in the informal part, we now see them as the graphs sort of induced by a structural causal model. Yes, there's a question? Yes, you. X1. X4, because of the self loop. I think it's on the next slide, or maybe in a few slides from now, you will get an example. Because this is a tricky thing, these self loops. But you'll get an example. Yeah, that's one way how they can arise. Excuse me? Okay, so bidirected edges don't point, you don't get a bidirected edge pointing from a node to itself, no. So you only get a bidirected edge between two different endogenous nodes when they are both dependent on some exogenous variable. Yes? Can it model, and then I didn't understand it. What kind of relation? Bidirectional. So you mean if the environment causes the system and the system causes the environment? No, that's excluded. That's sort of very strongly built into the notion of structural causal model. You can only get a causal influence from exogenous to endogenous. No, you don't. So this is maybe a bad example because it may suggest this, but the number of exogenous and endogenous can be arbitrary both. Yes? You mean, suppose we have one exogenous variable that influences three different endogenous ones. Yeah, then they all share, then each pair of them shares this one. So you get three bidirected edges. So it becomes completely connected. No, we don't. So in this graph, pointing doesn't help. Okay, in the graph where we don't depict the exogenous variables explicitly, we can't see whether, say for example, x1 and x2 here, whether they share just a single exogenous variable or 10 different ones. That's not clear. But actually, that's in a way that's a strong point of this graph. Because in the end, that's not really something that we need to model in many cases. So basically, the graph abstracts away from the latent, from the environment. So it's actually a feature that we don't see this in the graph. Yes?
Extract information about conditional dependence from this graph.
Yes, so that will be a topic for later. This graph will give you a Markov property, and thereby you can read off conditional independencies between the variables. That's a very important thing. Yeah. Okay, so here are just the general definitions. Maybe it's good to stress that that here, for example, x2 is called a parent of x3 because the causal mechanism for x3 depends on x2. So in the graph, you just say x2 is a parent of x3, or the other way around, x3 is a child of x2. And we can now distinguish exogenous parents and endogenous parents, etc. Here's the formal definition for the augmented graph and for the graph, but I think the example is clearer than these hard to parse definitions. Okay, here's a sort of a technicality that's important if you want to deal with cycles, and this is about the solvability. So basically, these structural equations, they are equations, so they can have, so if you just consider a set of equations on some variables, then sometimes they can have a solution, a single solution, unique solution, or they have multiple solutions, or they have no solutions at all. We will deal only with sort of well-behaved structural causal models that will always, whenever we try a subset of, whenever we solve a subset of these equations, we will get a unique solution. So that's this property here, unique solvability. So basically what we will be assuming is that if we pick any arbitrary subset of the structural equations, then we will, and we solve it for the endogenous variables, in terms of the exogenous ones, we'll get a unique solution. So in this example here below, we have three structural equations. If we solve the three, well, if you only look at the first equation, it has many solutions, of course, right? If these are real numbers, then we have any real number solves it. If you look at the third equation, it has no solutions. The second equation, if we solve for x2 in terms of x1 and x3, you can just solve it. It's already, you don't need to do anything to solve it. Has a unique solution. If we specify x1 and x3, there's only one possibility for x2 to satisfy the equation. So this one is this set of equations is uniquely solvable with respect to x2. But if we throw in one of the other two equations for x1 or x3, then it's no longer uniquely solvable. So if you pick any other subset of these three equations, other than the set consisting only of the second equation, you don't get a unique solution. Yes?
What does a plus mean?
Oh, these are real numbers, so plus is just adding two real numbers. Yes?
The last equation is not satisfied.
Yes.
Why? So that is by definition not a causality. So this should not be connected to any arrow shape, to any edge.
Well,
Because it's never, I mean, you can never.
so if you look at the third equation, it's a funny one because this is one where you get the self loop. So because on the right-hand side, we have a functional dependence. So on the left-hand side, we have x3, and then we have to write it as a function of its causes. In this case, it has one cause, x3, so it's causing itself. So this is a self loop. And you can actually get into these models, for example, by looking at dynamical systems at equilibrium. Sometimes you encounter equations like this, and then it's not, you know that there's no equilibrium solution. I mean, if I would replace the 1 by a 0, then it would have a solution, right? It would have many solutions. So if the 1 is not just a fixed number 1, but suppose this says x2, then you get the complication that if x2 is 0, then the third equation has solutions, and if x2 is non-zero, then... So you can get all kinds of complicated behavior of these solutions. And here we just say, well, in principle, anything could happen, and this may make things complicated. So here we will always assume unique solvability of any subset, and that will make our life easy. But you may run into these models sometimes. So, like I said, for simplicity, we will only use in this tutorial a special subclass of structural causal models. I call them simple because they make life simple. So an SCM is called simple if it is uniquely solvable with respect to any subset of the endogenous variables. And here is one small lemma. If the graph is acyclic, so if it doesn't contain directed cycles, then it is simple. Does anybody has an idea why that would be the case? Right, so if it's acyclic, then you just start sort of at the root nodes and you start solving the equations one by one, and you will never run into a possible contradiction because there are no cycles. So by recursion or by induction, you just solve it. You get a solution. Yes? If one of the f's is, yeah, we are not optimizing anything here. So the notion of convexity is not.
So for instance, f is like a double-lumped function or something. So one state depends on. Would it always be possible to uniquely identify the state?
No, so these can be, in principle, these equations can be arbitrarily complicated. So you can get equations like x squared equals y, which would give you two solutions for, well, the other way around, y equals x squared, this, you can get any kind of equations in principle, but if we check that they will always be uniquely solvable with respect to any subset, then we don't need to think about the solvability anymore. Yeah, so in a way, the class of simple structural causal models extends the class of acyclic structural causal models that you see a lot more in the literature, by allowing for cyclic causal relations as long as they are sufficiently weak to lead to unique solutions. But they still preserve much of the simplicity and convenience that's nice about acyclic structural causal models. And if you will go into non-simple structural causal models, then your life gets more complicated. Yeah, and there's just as a remark, modular SCMs that have been introduced in the literature, they are examples, or you can get them from simple SCMs. Perfect interventions. Let's see, what is the time doing? Yeah, so remember the perfect interventions. So I introduced these structural causal models, but I didn't tell you how to model changes yet. So why is it causal? Here's the answer. So we saw this concept of perfect intervention. We externally force a subset of the variables to take on a certain value without changing the rest of the system. Now, we can easily model this in a structural causal model by just updating this function, this causal mechanism. So the component, so if we intervene on some variable, then we just have to change the structural equation for that variable to become xi equals xi, where the xi is the intervention value. And if we don't intervene on the variable, then we just keep the original causal mechanism for that variable. So we only update the structural equations for the variables that we intervene on. And this basically, the interpretation is that we override the standard causal mechanism that determines the value of those variables by some other mechanism. So here, in the car example that we just saw, we can, for example, intervene by charging the battery. So this would be the intervention do x equals 1. And as you saw the previous, so without the intervention, the structural equation for x reads x equals ex, this sort of random environmental influence that determines whether the battery is charged, yes or no. That is overridden by x equals 1, because we really intervened to charge the battery. Or another intervention that you could consider is losing the key. Then basically you're overriding the equation for S. The car won't start anymore, no matter whether the battery is charged or whether the start engine is operational. Right? And also losing the key does not really change whether the battery is charged or whether the start engine works, so it's kind of a perfect intervention. And as you can see, it has an effect on the graph, the effect that we saw before. For example, the intervention on S, then the incoming edges on S, they are removed because, well, the function here no longer depends on those variables. Is this clear? Because if everything is clear so far, then sort of you have understood the basic definitions of structural causal models, which is a good starting point for the rest of the talk. Yes? Because ES is basically the environmental, yeah, okay, so you might, it depends on what ES exactly represents. But, okay, can we think of any other factors, whether the car starts or not? Maybe whether the tank, the gas tank is empty or not. If you have no gas left, then your car won't start. And by losing the key, you won't change that. So if ES basically expresses a summary of everything that may influence whether the car starts or not, then by setting ES to something, then you sort of, and here it doesn't make a big difference, but suppose ES is actually also influencing other variables, then that's where things become different. Excuse me? Oh, you mean it's not part of the system? Yeah, so this is always what you run into at some point when you start to interpret a structural causal model. So it's just a mathematical object. So for every perfect intervention that you can define mathematically, you can think about how can we realize it in the real world. Well, a perfect intervention on S, one way to realize it is losing the key, but there are many other things, right? The important thing is losing the key has an effect on whether the car is sort of here. You really directly influence whether the car starts or not, but you don't influence whether the battery is charged or so. And your question about why not intervene on ES, well, this is, by definition, we will only consider interventions on endogenous variables. So it's even excluded by definition of this framework. You could, of course, extend the framework to allow for that, but okay. Sorry, excuse me? Oh, often every endogenous variable has an exogenous variable, but not necessarily always. For example, if this is a deterministic relation, right? If we want to say that the car starts, that whether the car starts is really just the end of x and y, is a deterministic relation, then we don't need ES, for example. I don't really understand the question. I'll move a bit closer. Maybe that helps.
Okay. So for example, if the initial system provides that cars couldn't move in both directions on the crossroad, according to formulas, etc., and we apply the intervention that x1 is equals to 1, so the cars moves in this, and x2 is equals to 1, so we create an impossible situation. Do we care about this?
Okay, yeah. So that's a very good question. So maybe without doing an intervention, the set of structural equations has a unique solution always. So you had a particular example, but I will just phrase the question more generally. Now, if you do a certain intervention, then it can be the case that you no longer have a solution, or that you encounter a situation that you think that's not really modeled by the system anymore. So in general, yes, this is possible, but in this class of simple SCMs, we know that at least for perfect interventions, that won't happen. So in a way, that kind of situation is excluded. You don't need to exclude it, but then you're outside of the framework of simple SCMs, and you have to be more careful with setting up the whole theory. Yes?
The set of parents of node is not always unique, right? If you have a node that doesn't have any exogenous inputs, and you have other nodes that have a perfect, you may have other nodes that have a perfect functional relationship with that. So does that make a problem with the definition of uniquely solvable?
Yeah, I mean, you could say that x is a deterministic function of y. For example, x equals y. And then if you also say y is a deterministic function of x, for example, y equals x plus 1, then you have
If you say that y equals x, then you know that also x equals y, right? Or is that not?
yeah, so indeed. So if you have deterministic relations, it imposes.
Z equals x, and you can also say z equals y.
Yeah, so deterministic relations, you have to be careful with them, because they may sort of constrain other parts of the model. So you're once you have one deterministic relation, you have to be more careful in choosing the other structural equations such that you will always have this unique solvability. So that's why in practice, people often work with non-deterministic relations. If every endogenous variable has some noise source, like in the car example, then it's easier to avoid contradictions. Yeah, that's true. But suppose you want to use a structural causal model to model some computer program, which is also basically, you can look at all these structural equations as assignments within a computer program. As long as the structure is acyclic, that's another way to avoid contradictions. Right? So if you first write x equals y and then y equals x plus 1, then just by basically computer code is inherently acyclic because it sort of proceeds top down, and that's another way to avoid contradictions. Yeah. Yeah, indeed, why it's perfect. There are also imperfect interventions, so you can model all kinds of interventions. So for example, with the domino stones example, if there's an earthquake, you could consider it an intervention, but it's not really focusing on one particular stone, it just sort of does something with the whole system. Or maybe if it's a local earthquake with part of the dominoes or whatever. I mean, there can be any type, we can talk about many different types of interventions on the system. Perfect also here means that the intervention perfectly sets these variables to a certain value, but this may also be stochastic. Maybe there's uncertainty in the value, or maybe we only slightly change the values in some direction, or maybe we just perturb the system a little bit, but we don't know exactly how. So there are all kinds of interventions that you could consider, but these ones are perfect because it's hard to sort of be any more focused and sort of hard than these perfect interventions. Surgical is because they also remove the incoming edges. Okay. Here's another example of an intervention. And quickly look at this. So here the observational structural causal model. Then if we intervene to set x3 to the value xi3, the only thing that changes is this particular structural equation for x3. And in the graph, we remove the incoming edges on x3. Okay? Now, I said that we will not define causality in terms of probabilities, but we'll do it the other way around. So, so far we had all these structural equations and the exogenous distribution. And we talked about this notion of a solution of a structural causal model, which are random variables x and e that satisfy the structural equations and the prescribed exogenous distribution. If we have a solution, x comma e, then we call the distribution on x the observational distribution of a model, or a observational distribution, because if there are multiple solutions with multiple distributions, then we could have multiple observational distributions, or we can have none. But if we restrict ourselves to simple SCMs with this unique solvability property, then actually the observational distribution exists and is unique. So that's nice. So the SCM basically induces a unique distribution on the variables x, on the endogenous variables. And that is denoted in this way. If so, the density of that distribution with respect to some background measure, we denote it as the density of x according to this model M. Okay, well, this was the observational distribution. We can do any perfect intervention on this SCM. And then basically what we get is an interventional distribution. So we get a whole family of interventional distributions defined by the SCM. For any subset of the endogenous variables and any value that we can give it, we get a distribution on the entire set of endogenous variables. And again, the nice thing is if the SCM itself is simple, then each interventional distribution will exist and will be unique. And following Pearl, we will denote them as the density of x given do xi equals xi I. So if you have read Pearl's work or some of Pearl's work, or you may have seen this do operator at other places, that's what it denotes. And so basically you can see here that the crucial difference between a structural causal model and other statistical models is that we simultaneously model a whole family of of distributions, namely the observational one, and for any perfect intervention, the corresponding interventional distribution. So this single SCM object models a lot of distributions simultaneously, corresponding to how the system reacts to different external changes. Okay, what's the time doing? Okay, self loops. There was a question on examples of self cycles. So here you see one. If we have a free market and we have quantities like price, supply, and demand, then usually in economy textbooks you will see models like these where the supply depends on the price, the demand depends on the price, and then if there's a free market or a perfect market, then the price will adjust itself until supply equals demand. So here is a structural causal model version of this model. So here we have three structural equations, one where supply is a function of the price and some exogenous influence, ES. Demand is a function of the price and some exogenous influence, E of D. And this is a somewhat funny looking equation. The price is a function of price, supply, and demand, which is exactly such that actually the price cancels out of this equation. So this is because P occurs on the right-hand side, we have a self-cycle. But it's a somewhat funny one. We can't actually rewrite this equation in some way to get rid of this self-dependence. So sort of this is then also a sign, this self-cycle, that this is not a simple SCM. So for the rest of this talk, we will not look into this anymore. So luckily, simple SCMs, they can't have self-cycles, so that's, well, unluckily we exclude systems like this, but well. Yeah, and we had, remember I sort of started with this informal definition of direct causality. We can now formalize this using a simple SEM. So if we have a direct edge I to j in the graph of an SEM, then we just say that I is a direct cause of j according to this SEM. So this is the definition, but it matches our intuition, basically, about direct causes in the following sense. This is a proposition, well, it's a bit hard to read, but basically what it says, if we intervene to set all the variables to some fixed value, and we intervene also on variable I, and we use two different values, then we actually get different distributions for xj. Right? So if we fix everything and we turn this knob, then we can see something changing here. Then there's a direct causal effect of I on j. And so this is a sufficient condition for there to be an edge from I to j in the graph. I used to think that this is the definition of direct cause, in the sense that this is a necessary condition as well, but that's interestingly not the case. So sometimes you can infer that there must be a direct edge in your structural causal model from I to j, but you don't see it by playing around with I and looking whether the distribution of j changes, even while fixing all the others. A similar definition or a similar notion for sort of indirect causation. So if there exists a path in the causal graph, in the graph of an SEM, starting at I and following directed edges, we end up at j, so I is an ancestor of j, then we call I a cause of j according to the structural causal model. And now it's a little bit simpler. We don't need to fix all the other variables. Now, if we just give I one value or another value, and we see a change in the resulting distribution on xj, then we know that there must be such a directed path from I to j, so I causes j. Again, this is a sufficient condition, and a necessary condition is not known in general. Finally, the bidirected edges, they also get a natural interpretation in a way. So if there's a bidirected edge then in the graph of an SCM between I and j, then we say that I and j are confounded according to the model. And now basically what this says is that if we intervene on all the other variables to fix them, and if we see a difference between the observational distribution of xj given xi and the interventional distribution, so basically in other words, causation is not correlation, then I and j must be confounded, so we need an edge, a bidirected edge between I and j in the graph. So basically now these three theorems, they connect SCMs and their graphs with these informal interpretations of causality that we started out with. And let me see, how much time do we have? Yeah, I'm going a bit slower than I anticipated, but that's fine. I'll just continue a little bit with my lecture throughout the first tutorial session. The notion of marginalization, that's the last thing I will discuss before the break, and also for today. So, a very nice feature of structural causal model. Okay, so if you have a probability distribution, that's basically sort of a description of a system, you could say, and we have this notion of getting a description for a smaller part, a subsystem, just by marginalization, right? We just integrate out over the variables that we are not interested in. So we have a model of a big system, and we project it down to a description of a small system. You can do something similar with structural causal models. And this is an example. We call this a marginalization in analogy with a probabilistic operation. Suppose we start with this structural causal model. We have seen that one before. Now suppose we marginalize out x2 and x4. So we want to get rid of the description of x2 and x4 in our model. Well, we can do this basically by substitution. We solve this function, we solve the two equations for x2 and x4. We solve them explicitly in terms of x2 as a function of the exogenous variables and x4 as a function of the variables, and we substitute those into the equations for x3 and x5. Then we get this basically with this graph, and that's an example of a marginalization. So let's look a little bit more in detail at what happens here. So if we have an SCM M and we have a subset L, so L stands for latent, we want to make the variables in L latent. And O is the rest of the system, that will be the observed part. Then we can start from all the structural equations like this. We can write them as the two components, L and O. And now we can solve this, if we can solve this part explicitly, so that the right-hand side no longer depends on XL, we can substitute that into the other equation. And then we have written the second equation without any dependence on XL. So we can actually sort of forget the first equation, and then we get basically the marginalization. So basically, whereas in probability theory, marginalization is the operation of integrating out what we are not interested in. Here, it's a matter of substituting, well, first solving and then substituting out what we are not interested in. And we can also do this marginalization on the level of the graph. So here's a formal definition, but in terms of the example, basically you see that here we can start at x1 and then we can follow the edge through the latent part, x4, and end up at x5. So after marginalizing out x4, we need actually a direct effect of x1 on x5, because we are no longer able to say that it's actually an indirect effect mediated through x4. So this also connects with one of the questions in the beginning. Yeah, and something similar for bidirected edges. Here, this part gives a bidirected edge between x1 and x3. So you can sort of, here's the formal definition for what happens in general. Now, why is marginalization, why is this a nice operation? Well, because it satisfies nice properties. The important one being that it preserves the causal semantics of the system. So any intervention that we do on the remaining part of the system, on this marginalized SCM, the interventional distribution that we get is basically the same as on the original model, but then restricted to the observed part. So this is just a long way of saying that basically you preserve the causal semantics, you preserve your probabilistic description, everything is preserved, except that we have restricted what we can say to a smaller part of the system. Graphically, what you get, this graphical, yeah. So what is nice about the graphical marginalization operator is that it sort of also indicate, you don't even need to look exactly at the equations. You can just do the marginalization on the level of the graph, and then you will be able to see the causal structure. You can read it off from the marginalized graph. So the graphical marginalization is compatible with the one on the level of the equations. And also very nice, the marginal, if we start with a simple SCM and we marginalize it down, what we have is still a simple SCM. So the class of simple SCMs is closed under marginalization. Yeah, and why is it nice to have a class that is closed under marginalization, basically it tells us that we don't have to model. So you're always forced to, if you're doing causal modeling, you're always forced to consider the variables that you want to model, the endogenous ones, but also exogenous ones. And maybe the exogenous ones have also causal relations with each other, and so basically you would have to consider larger and larger causal models. But because the whole thing is closed under marginalization, we can sort of basically forget about all the intricate details of the environment. We can just focus on saying, well, this is a system I want to model, and you get an effective description of that system. Okay, that's it for today. Tomorrow we'll continue here. Are there any remaining questions before the break? Is it actually time for the break? I'm already over time, so maybe we stop here, and if there are questions, you can find me here or ask them tomorrow.